Okay, welcome to Unit 4 on forces. We define forces as any push or pull, and we know that all forces must involve at least two objects. Oftentimes this is forgotten for objects such as a ball that's thrown. As the ball's in the air, I'll have students that tell me that the forces on the ball are gravity pulling it down, which would be the earth pulling on the ball. And then they talk about the force from the throw that's keeping it going. And unless the hand is still touching the ball, then there's no force from the throw. So we can't have a force without two objects. And if you can't think of a second object, then there's no force. The example would, of course, be a contact force where the objects are actually touching each other. Long range or field forces involve forces that exist without the objects touching. Examples of this would be gravity being the attractive force between any two masses. We typically think of gravity having to do with the Earth pulling on objects or other large bodies such as the moon or the sun or the planet pulling on objects. And that's because gravity is determined by the mass of the objects. But the truth is that all masses pull on other masses with some sort of gravitational force. Typically, we don't notice it because the masses are fairly small. Other long-range or field forces would be things like magnetism or the internuclear force that holds protons against other protons within the nucleus of an atom. This is actually a non-contact or long-range field force. Likewise, the force exists between protons and electrons to hold them in orbit. Anytime we're discussing forces, we usually discuss inertia, and later we'll talk about Newton's laws, and we'll talk about the law of inertia. But inertia is essentially an object's resistance to any change in its current state of motion. So if it's moving, it tends to keep moving, and if it's at rest, it tends to keep at rest. And the mass determines the inertia, at least the rest part is what we say. Later we'll talk about momentum being mass and velocity. And when we talk about an object at rest staying at rest and an object in motion staying in motion, the staying at rest is defined typically by its mass, but an object in motion staying in motion typically is defined by its mass as well as its velocity. Just as a reminder, make sure you keep separate the difference between mass and weight. Mass is the amount of matter, and I like to say stuff. The amount of matter that's in an object is measured in kilograms as the base unit, or the SI base unit. Weight is a measure of force, so weight can change based upon how hard an object pulls on another object. Typically with weight, we talk about the force of the Earth on the object, but weight can, of course, vary depending on your location on the Earth, or obviously an object's weight would be different if it were located on a different planet or on the moon or whatnot. So weight and mass are slightly different. Mass never changes. It's the amount of matter that's inside of the object, and weight is how hard that matter is being pulled on. Volume is, of course, the space the object occupies, and we usually measure that in liters, but for SI calculations, we typically use meters cubed. Please don't forget, and I will remind you, weight is a force, weight is a force, weight is a force, weight is a force. So when we're talking about calculating weight, we'll of course use the force equation F equals ma, or F equals Fg, g being the acceleration due to gravity. When talking about friction, we have to talk about talking about forces, we always talk about friction. Friction is a force which resists motion or attempted motion. Oftentimes we leave out the attempted motion. Sometimes when an object doesn't move, it's because of the force of friction. Keep in mind that air resistance is a type of frictional force. And friction doesn't always slow down an object. Oftentimes friction makes it speed up by less. It reduces the acceleration amount while the object is still speeding up. Air resistance is a great example of this. When an object's falling, air resistance does not make the object slow down initially, it just makes it speed up by less. Now, if the object were to change shape, change the amount of air it's passing through, such as a parachute popped out, then we would talk about the force of friction causing the object to slow down in that case. We've talked about resultant vectors, so you should have an idea of what a net force is. We've talked about net speed and net velocity. Net force is just the sum of all forces that exist on an object. Remember that adding forces doesn't always mean mathematically adding. We're talking about the addition of vectors, and that may involve other geometric manipulations when we talk about adding different forces. Forces are these vectors, they're vector quantities. So adding if two objects or two forces are being applied, parallel or anti-parallel have different meanings. Likewise, if we have a force at a 90-degree angle to another force, then adding those two forces would involve use of the Pythagorean theorem. Occasionally, if they're at odd angles, we may have to break these things down to their components before adding them, or you may use the law of sines and cosines in your vector addition. I like to call these my important facts about forces that often people get confused on with conceptual questions. First one, if an object is not moving, the net force on the object is zero. That's usually fairly obvious and no one has trouble with that. However, number two, if an object is moving but not accelerating, remember that the net force on the object is zero. Or in other words, constant velocity equals zero net force. So again, if the object's not accelerating, it's because there's no net force. An example of this, we always talk about the ball that's thrown in outer space. It'll keep going forever. And why does it keep going forever? Well, there's no force on it. There's nothing to slow it down, nothing to make it change direction. So you throw the ball in outer space and it'll keep going, and it never stops. The third one that goes along with that is that forces do not have to exist in the direction an object is moving, and often they will be in the opposite direction of the motion. Example of this, I roll a bowling ball down the bowling alley, and the ball is rolling forward, and typically students want to draw a force that's pointing forward while it's rolling. And in reality, the forces are actually up, down, and backwards. That's forward would be the only direction that there isn't a force, and we'll talk about that when we do our force diagram. But the forces on the ball after it's being rolled, we push on it, of course, initially to make it roll, but once it's rolling down the bowling alley, there's gravity pulling it down. Why doesn't it accelerate down? Well, because the floor is also pushing up on it, and we call that the normal force, and we'll define that later. And why does it slow down slightly? And on a bowling alley, there isn't very much friction, but why is it slowing down? Well, because there's air resistance and friction pushing backwards on the ball. Okay, so out of the direction of the motion is the only direction that there isn't a force in. There's forces up, down, and backwards, but there is no force pushing forward. Force abbreviations we'll commonly use FW or FG. I'll use FG more often, but it's the same thing. Weight or gravitational force are the same thing. So when we talk about an object's weight, or we talk about the force of gravity on an object, those are the same thing, and they're always directed downward toward the center of the earth. The normal force is that push in the other direction. So if I have an object sitting on a table, the earth or gravity is pulling that object down. And why doesn't it move down? Well, it does not move down because the table is pushing back up, and those two forces cancel each other so that the object does not accelerate. And the upward force from the table would be what we call the normal force. Normal force is a force that exists that's perpendicular to a surface that an object is in contact with. So remember, if an object's falling through air or through space, there is no normal force. There is no surface it's in contact with, and that's why it's accelerating, because nothing's pushing up or holding it up. With nothing holding it up, the net force is down, and therefore it accelerates down. The ball sitting on the table, however, has that same gravitational force down, but it also has the force of the table holding it up, and therefore it doesn't move or accelerate. Other force abbreviations, FF is the frictional force, and sometimes you'll see that written as a script F as well, and I'll show you that in class oftentimes when I'm doing calculations, I'm sure. But remember that air resistance is also a frictional force. The tension force will be labeled as a capital T, but sometimes as FT with the subscript of T, and that's a pull that exists from a rope, a chain, cable, anything else. Even solid objects such as beams or boards can have tension forces when they're being pulled instead of pushed. And of course, we defined that before, but a net force we label as F net. Oftentimes, you'll see that with a summation symbol, where it will show the sum of the forces that exist on an object instead of F net. No discussion of forces would be possible without discussing, of course, the most famous implications of forces, which are Newton's three laws of force. The first of Newton's laws being the law of inertia, and we kind of talked about inertia before. It says that objects at rest tend to stay at rest, and objects in motion tend to stay in motion. And the big kicker here is unless acted upon by a net force. And the example I always give is, well, objects in motion stay in motion. Well, if I roll a ball, I know the ball eventually stops. It doesn't stay in motion. I think, what was Newton thinking of? but of course, in this case, it's acted upon by a net force. Force being friction, so when I roll a ball, if there were no friction, it would continue to go forever, and that's the example I gave of the ball that's moving in outer space, where there's no air resistance or other forces to slow it down. But of course, on Earth, my ball that's rolling will slow down because there is a net force, and that force is greater or less depending on how much the friction is. Other parts of Newton's laws that people forget about are the second two parts. Motion always occurs in straight lines, so we're used to the objects at rest staying at rest and objects in motion stay in motion, but motion always occurs in straight lines, again, unless acted upon by a force. So that ball in outer space will keep going, and it'll keep going straight unless something makes it curve. And motion always occurs at constant velocity. It's kind of the same thing we discussed. It's not going to speed up or slow down unless there is some net force acting upon the object. Newton's second law describes the relationship between force, mass, and acceleration. In equation-wise, it's of course the famous F equals ma, but it says that net forces cause accelerations, and so if there's an acceleration, there has to be a net force. Likewise, if there is a net force, there has to be an acceleration. And as well, it tells us that net force and acceleration are always in the same direction. Now, that's not necessarily in the direction of the motion, as we've discussed before. Net force on an object can be in any direction, and when we're talking linear, of course, a simple example of that is when an object's moving to the right but slowing down, then the net force would be to the left, and that net force would usually be a frictional force. Newton's third law we refer to as the law of action-reaction. It says anytime an object exerts a force on a second object, the second object must exert the same amount of force back on the first object. Or in other words, I like to say if A hits B, then B hits A. Or define-wise, you can say a force can't exist by itself. In other words, all forces occur in pairs. Newton's third law is easily proven. If you need to prove Newton's third law, a little experiment you can do is go find yourself a bowling ball or a brick, set it on the ground, and then kick it. And you will apply a force to the ball, and you'll notice that the ball applies force back to you. And if that's not enough to convince you, if you're a little more difficult of a learner, then the second step or second part of the procedure is to kick the ball harder, and you'll realize that it applied a harder force to you. So when you apply a greater force to the bowling ball, it applies a greater force back. Good proof for Newton's third law in case you're a little skeptical. So when we're identifying action-reaction forces conceptually, it seems pretty straightforward, but oftentimes we make mistakes because we don't follow through with step one that says, first of all, you have to confirm that there's an interaction happening between two objects. Remember, there has to be two objects for any force. So if there aren't two objects, you don't have a force. So you first have to confirm there's at least a force between two objects. Second one is to just simply find an object A that's pushing or pulling an object B, and the conclusion therefore is that the object B must also be pulling or pushing on object A, such as the bowling ball that's falling. There's an action and reaction force pair for that. The bowling ball is falling, being pulled by gravity, so we call gravitation the action force. And then there has to be a reaction force. So if you're going to identify the reaction force, you have to first identify the two objects. When the bowling ball is falling, the boulder, when the boulder, or bowling ball for that matter, is falling, the earth is pulling on the object, and therefore the reaction would be that the object pulls back on the earth. So we've got boulder being pulled down by the earth, and earth being pulled up by the bowling ball, or the boulder. I don't know why I keep changing my boulder to a bowling ball. The typical question here is, well, if the earth pulls the boulder down and the boulder pulls the earth up, how come both of them don't move? Well, remember with Newton's second law, it says that F equals ma, therefore the acceleration is inversely proportional to the mass. So when the earth pulls on the boulder accelerates. When the boulder pulls back on the earth also accelerates, but the acceleration is extremely small because the mass of the earth is extremely huge. This shouldn't be too difficult to understand if you think of a simpler object. If I hit a hockey puck with a stick, the hockey puck's going to accelerate. If I increase the mass of the hockey puck from about 40 or 50 grams to about 50 kilograms, I can apply the exact same force to the hockey puck, but it's going to accelerate a lot less. So the forces are equal on the bowling ball, There's my bowling ball again. Forces are equal on the boulder and the Earth, but the boulder accelerates greatly because it has a small mass, and the Earth accelerates very small because it has a big mass. One important thing to remember here is that action-reaction forces never cancel each other. And why don't they cancel each other? Because they're on different objects. This is oftentimes conceptually a little perplexing. Example I usually give is that if I have a cart and I push on the left side of the cart with 5 newtons of force and you push on the right side of the cart with 5 newtons of force, that the two forces are equal and opposite to each other, and therefore they cancel each other and the object doesn't move. When we look at this picture of the boulder, there's a force upward that's equal to force downward, and the idea is, well, don't those two forces cancel each other? And if they did, then we'd say the boulder never moves. I also like to give a soccer ball example. When I kick a soccer ball, I'm applying a force to the soccer ball, and Newton's third law says the soccer ball applies an equal and opposite force back to me. Those two forces are equal to each other, they're in opposite directions, and so they cancel each other, and you can never kick a soccer ball. So any of you that play soccer might as well quit. It's impossible to kick a soccer ball because the force forward on the soccer ball is equal to the force backwards, and they cancel each other. Now, what's the problem with that example? Well, the two forces aren't on the same object. In my first example with the cart, I apply a force of 5 newtons to the right on the cart, and you apply a force of 5 newtons to the left on the cart. Both those forces on the cart are 5 newtons. And the force on the cart, or net force on the cart, is 0 because both those forces cancel each other because they're both on the cart. Let me be a little more emphatic. With the soccer ball, or this boulder that's in this picture, there are two forces, and they are equal to each other, and they are opposite. But with the soccer ball, one of the forces is on the ball, and the other force is on my foot. And so the ball does accelerate because there is a net force on the ball. And my foot also accelerates because there's a net force on my foot. The ball speeds up, my foot slows down. Same thing in this picture. There's two forces. They're equal, they're opposite, but they're not on the same object. One's on the boulder, the other's on the Earth. So the boulder accelerates and the Earth accelerates. The only way to cancel a force on a boulder is with a force in the other direction on a boulder. With my soccer ball example, the only way to cancel a force to the left on a soccer ball would be for somebody else to kick on the soccer ball to the right. And those two forces would then be both on the soccer ball and would cancel each other because they are on the same object. So for two forces to cancel each other, they have to be on the same object. So action-reaction forces never cancel each other because they're always on different objects. A pushes on B, B pushes on A. One of the forces is on A, and the other force is on B. So terminal velocity for a falling object, you've heard this term before. Terminal velocity is the velocity at which an object will no longer accelerate. Terminal velocity is the maximum velocity. It's a point at which net force equals 0 because the force of gravity down is equal to the force of air resistance up. In other words, as this object falls, it goes faster and faster, and we know when objects go faster that air resistance gets greater. If you're not sure about that, I have another experiment. When you're driving in the car, put your hand out the window and you'll feel some air resistance. When you drive faster and put your hand out the car window, you'll feel more air resistance. Of course, do not try this at home. You're not supposed to put your arm out the car window, especially if you're near a telephone pole. So here's an example of falling ball and how air resistance builds up on the object. When I first let go of the ball, we have a force of gravity that's pulling down on the ball. It's negative 15 newtons in this example. It just started falling at t equals 0. In other words, I just let go of it. So the air resistance or frictional force is 0 on it, and therefore the net force is 15. Now, if I look at the ball 2 seconds later, it's had a chance to speed up a little bit because of acceleration due to gravity. So there is a little air resistance against it. Let's say that air resistance is 5 newtons. You got gravity pulling down with 15, air resistance pushing up with 5. And the net force is now negative 10 instead of negative 15. In other words, the air resistance is canceling a little bit of our gravitational force. Is the ball still accelerating? Sure it is. Is it accelerating as much as it was before? No. So at t equals 0 seconds, our acceleration was exactly negative 9.8. And at t equals 2 seconds, the acceleration is reduced to maybe, I don't know, negative 7 or negative 6.5. Point being that the ball is still speeding up. Okay, so air resistance is not making the ball slow down. The ball is still speeding up. It's not speeding up by 9.8 anymore. It's speeding up by less. So it's still speeding up, it's just speeding up by less than it was previously. When we get to a time of, say, 4 seconds, you can see that the air resistance has gotten a little greater. It's still speeding up at 2 seconds, so at 4 seconds it's still speeding up. And if it's still speeding up, then the air resistance force gets greater. If the air resistance force is getting greater, we are canceling more of the gravitational force and the net force is getting smaller. If the net force is getting smaller, the acceleration gets smaller. Then finally, at time equals 6 seconds, we're at the point where the gravitational force down is equal to the air resistance force up. In other words, it's going so fast that the air resistance has gotten great enough that it cancels the gravitational force. Net force is 0, and it doesn't accelerate anymore. So notice my black vector has gone from negative 15 net force to 0 net force. The net force has decreased on the ball, therefore the acceleration has decreased until it reached 0. This ball will continue falling at a constant rate, constant speed, unless it somehow changes shape, like we discussed earlier. Let's say a parachute pops out of the top of the ball, changes the shape of the ball, or changes, in other words, the amount of air it's pushing through or plowing through because it's gotten wider, and then the air resistance would increase. But at this point, the air resistance can't get any bigger, so the ball will never slow down. It just continues at constant speed. Just to reiterate, as an object falls, its velocity increases, the net force decreases, and the acceleration decreases until it reaches terminal velocity. These are conceptual questions you see over and over on any physics test, but especially on the AP exam, where they'll test you on these 3 things, and you need to make sure you keep them straight and why they are what they are. Okay, so this summarizes our most basic information on forces, friction, and terminal velocity. Those would be the 3 main things. From this point forward, the things you're going to need to really know about would be force diagrams, especially for systems where multiple masses are moving. We'll discuss a lot of those in class, and I'll also have some other tutorials that discuss those and how to calculate the net force on, let's say, 2 objects connected with a string or a cable or something like that. And, those are typical problems you'll see on the AP exam. So make sure you look for the next lecture in the sequence, or perhaps I'll discuss this in class as well, and we can get that information to you either way.